All right, last time we took a look at section 4.3. I believe we had gotten through with the greatest common divisor parts. Does that sound right? And let's see, where did my notes go? Oh, there they are. We were taking a look then at least common divisor, least common multiple. That's a typo on your sheet. That's just what happens when I have too many sheets. First time through, there's typos. All right, so we had gotten through example 4. Does that sound right? Okay. All right, so go ahead and fix the typo to start with, and I will go to my slide that has it on there, and I will fix it as well. Definitions. This is least common multiple, so please strike this out and put the right word there and the right abbreviations. This is least common multiple. Too much cut and paste. LCM. All right, so a least common multiple is the least non-zero number. Okay, so no zeros, no negatives, nothing like that. It's a positive number we're looking at here. The least non-zero number that is a multiple of all whole numbers in your set. And a really good remembrance for this, memory tool to think of is this is like the multiplication tables. Okay, at some point you probably memorized some sort of a list of the multiplication table for threes. It's 3, 6, 9, 12. Those are all multiples of 3 because they're in the multiplication table for 3. Okay? So that's what we're talking about when we're talking about multiples. We're talking about the numbers that are in the multiplication table or in the multiples list for any particular number. All right, we're going to look through several different methods for finding least common multiples. The first one does not have a direct correlation back to greatest common divisor. Some of them will, but this one doesn't. This is the number line method, or it's sometimes called colored rods. So what you're doing is you're going to show multiples of all numbers that you're given on a number line in the intervals of each value. And then you're going to find the first value at which the intervals coincide. So let me talk about why it has two names. Okay, so one way to do this is strictly from a number line point of view. So in other words, if you have multiples of, say, 5, okay, so if 5 is one of your numbers, then every 5 units you mark, 5, 10, 15, so forth on a number line. Okay, so that's the number line idea of what's going on here. The colored rods idea, which is a great manipulatives tool, you will find that you have these in many of your schools, is that you actually have physically colored rods. Okay, so they're like pieces of wood, and they have different lengths. So some of the pieces of wood are 3, and some of the pieces of wood are 5, and some of the pieces of wood are 2 and whatever. And they're actually colored different colors so that you can identify them more quickly. So all of the 2s are colored yellow, for instance, and all of the 3s are colored red, and all the 4s are colored blue, and whatever. Okay. So what do you do with those? Well, the idea is that you just stack them end to end. So if you had blocks for 5, you'd stack, let's say they're blue, 5 blue, and a blue block that's 5, and then you have another blue block that's 5, and another blue block that's 5, and you can keep sort of putting them in line like a train. Okay, so you're either thinking of that in terms of putting pieces of wood of length 5, right, all colored the same color in a row, or you're thinking it from a number line. And I'll draw both pictures on our example so you can see what it would look like visually if you're doing one. Okay, so let's do an example. We're going to use not 5, we're going to use 6 and 15 using the colored rods or number line method. And when you do this example, it doesn't matter which of these images you draw, but you are going to draw something on this particular problem, okay? So this is kind of a concrete model approach because you have an actual physical drawing or a physical object manipulatives that you're using. All right, so here's an example. We've got 6, so we've got 0. We have 6. What would be the next number after 6 that's a multiple of 6? 12. What's the next multiple of 6? 18. After 18? 24. After 24? 30. We'll do one more, and we're going to stop after 30. 36. And the first thing you should notice is I could continue to do this all day, right? And we could continue this list. And we don't necessarily know exactly how far we want to go when we're looking at the problem, especially when a kid's learning this for the first time. They're not going to know how far to go. So you go a distance out, and you stop, and you try and see if it works. And then you do it again. All right? I'm going to switch colors here just so that I can mark it differently. The next thing that I'm going to do is I'm going to do multiples of 15. So obviously we still start at 0, okay? And then the first 15 would be somewhere in between the 12 and the 18. What's the next multiple of 15? 30. And that coincides with a 30 I already had from before. Okay. If you wanted something else visually, you could actually show yourself moving the 6's at a time. And you can see that we end on 30. And if we're doing skip counts or jumps of 15, here's my first 15. That does not end at the same place that any of the black arrows did. But the second one does end at the same place that the black arrow did, the 30. So the whole idea is that at some point we land on the same number in our jumps. You know, one person's jumping 6 whatevers, the other person's jumping 15 whatevers. Where do they first end at the same location? Okay, so this is one picture of this. Everybody good with that? Okay, the colored rods picture, we're going to actually draw little rectangles. So I'm going to use, well, I'll keep the colors I used already. So I'll use black rectangles for my 6's, and then I'll use blue rectangles for my 15's. So we'll see how good I can do these. So this is 6. Here's another 6, and we're putting them end to end. So if we were really doing this in a physical diagram, we'd have these actual blocks that would be sitting side by side. Okay, so far I've got 5 blocks. I'll do 6 blocks, which gives me to 36. I'm not trying to say that this is the same length as my original diagram. I just drew the picture, okay? So I know it's not matching up quite right, but and then I've got my blue block that's going to represent 15. There's another one over here. It's going to go off my screen a little bit, or at least almost off my screen. And what we're wanting to do is we're wanting to see where they both end again at the same place. And right here is where they end at the same place. A blue block ends right there, the 1530, and my 5 black blocks of length 6 each end at the same location. So we could physically use pieces of colored rods to put them side by side or end to end to actually see where they both end at the same spot. Concrete model. When would this work well? Kinds of numbers. You're going to have smaller numbers to do this with. From a very practical sense, if you're using colored rods, you're only going to have the colored rods in small numbers, for one. But also, you don't want to draw this picture quite out, into the hundreds, right? I mean, that's going to be an impractical endeavor. We don't really want to deal with it from that perspective. But for small numbers, it works pretty well. And or numbers that simply have multiples soon enough. Like the numbers themselves might be large, but the numbers that they actually end up with their multiples don't end up being too far out, right? Like 15 to 30, I only had to make 2 jumps to do that, right? That's not too far out in terms of my list of multiples. All right, let's look at another list, another possibility. This is called the intersection of sets method. We saw this one before. The idea is that we list all the multiples of each value, and then we find the least value that the lists have in common. Now, flip back real quick to the front page. I think it's probably on your very front page where it talked about intersection of sets method for greatest common divisor. What's different in our descriptions here? What do you notice that's different? There's a couple things. Okay, so one of them is the divisor versus the multiple, right? The first one I did a list of divisors, all the numbers that divided it. Now I'm doing a list of multiples. That's that multiplication tables idea. The second one is the word least. In the first problem with greatest common divisors, I looked for the greatest number in their list that they had in common. And now I'm looking for the least number that's in the list that they have in common. All right, so let's do an example. You can see how it works. We're going to use the numbers 12 and 15. And we're going to make a list of multiples. So 12's first multiple is 12. You're always starting with itself. What's the next multiple in the list of 12's? 24. And we'll write out, I don't know, 5 or 6 of these. What comes after 24? 36. What's next? 48. Let's do 2 more. What's after 48? 60. 72. And just for fun, I know the next one's 84, so I'll write that down. That's 12s. 15. Well, it starts with 15. And we know what 30 is next because we just did 15 a minute ago. What comes after 30? 45. And then 60. And then, okay, and then we would have 90 if we kept going. All right, so we'll pause there. Once we have a number in both lists that they have in common, the first such number is my least common multiple. And that number in these lists is what? 60. There is no smaller number that is in both lists. So the least common multiple here is 60. And I realize we didn't actually write the answer out over here. I apologize. Over here the answer was that the least common multiple, of course, was 30. We just didn't write it down. And now my least common multiple for these numbers is actually 60. Okay, any questions on that method? Now again, this method has some drawbacks. This one works really well when they end up with a common factor soon, or common multiple soon, right? If those common multiples had been like the number we were looking at with the pirates example and had been something in the 3000s, this would not be a good thing to do, writing out these lists of numbers until I get to something in the 3000s. It's not practical, right? So it has some drawbacks. It does have the feature that it's very concrete. It fits the description exactly. It is a multiple, and I listed all the multiples, and it's the least one. So in terms of the actual description, it is spot on, very clear that this answers the question of what is the least common multiple, because I made a list of multiples and I found the least one. So that part of this method is actually really nice. All right, let's do a couple other methods that sort of have drawbacks into, or connections back into greatest common divisor. This one is prime factorization method. So go ahead and jot down all the fill in the blanks on this one, and then we'll talk through it. Let's do the same thing that we did on the other list. Let me talk through it, and then I want you to flip back to where we did prime factorization before and notice the differences. So this says that we're going to construct the prime factorization of each number. So we're going to get all the prime factors, factor tree, something like that. Then we're going to choose all the prime factors that are in each factorization. Then we're going to list each prime with the largest exponent in the factorization. And then we're going to find the product, that means multiply what we got in step 3. So where's the first thing that's different in this description compared to the greatest common divisor's prime factorization method? That's true. This says largest, and that said smallest. There's actually something in the line before that's a little bit different as well.
Is it the word common in the first one?
Yes. And what's it say here? Actually, I think here's probably the best word. This one says all. That first, for greatest common divisor, we wanted only the factors that the prime factors they had in common. Here we're going to have all prime factors in either of them, not just the ones that are in common. We're going to have everything. Okay, so we're going to get more when we do this, right? We're going to get more stuff. We're going to get larger exponents. We're going to get more prime factors potentially. We're going to get larger numbers. And I mentioned that last time, but let me mention it again. Greatest common divisors, the word greatest does not mean the number is big. It means it's a greatest divisor, and divisor means it's something smaller most of the time than what you started with. Multiple. Multiple means it is something larger than you started with, and least does not mean it's a small number. It just means it's the smallest big number, right? The smallest multiple that what we would be working with. Okay, let's do an example of this. You guys are really good at finding prime factors. I'm actually going to use 3 numbers here. There's nothing special about using 3 numbers or 2 numbers. I do want you to see that it works with both of them. Both of those ideas. So I'm going to do one with 3 numbers. So we're going to do 90. And I'm going to do my division method like I did last time. So what divides 90? What's the least prime that divides 90? 2. And that gives me 45. Now we did 45 last time. While I know it does divide by 5, there's a smaller prime it divides by. It's 3, which gives me 15. And that gives me 3 and 5. So the number 90 is 2 times 3 squared times 5. Everybody's good with that, right? We've gotten quite good at that. How about 50? What number will I divide by? 2, and that gives me, good, 25. And then I'll divide by 5, and that gives me 5. So this factorization is 2 times 5 squared. Yes, very good. The last number is 20. 20 divides by 2 to give me 10. 10 divides by 2 to give me 5. And so this prime factorization is what? 2 squared times 5. Okay, so far we have not done anything different yet in this problem than we've already been doing before, right? Exactly the same. So what's next? Well, we need to list all the prime factors that are listed in any number at all. So that's going to be the start of my least common multiple. What is one prime factor? 2. What's another prime factor? 3. And what's another prime factor? 5. Now we're not done, but that is all the, those are all the prime factors in any number. Some of them are present in more than one number, but not all of them. Okay, there doesn't have to be in every number, just those are in the numbers somewhere. So the next thing is the one that Jamie noticed was this idea of largest, right? I need to figure out what is the largest exponent on any 2. And what is it? 2. And it's right here, yeah? 2 squared. What is the largest exponent on any 3? Happens to also be a 2, and it's at the first number. And what is the largest exponent on any 5? 2. And that happens to be in the middle number. It wouldn't have to be that way. It could be anywhere in the problem. But we want the largest one that's there. And then we're going to multiply these together. 2 squared, 3 squared, 5 squared. If you want to simplify it before you have to deal with it, you could actually write this, of course, as 4 times 9 times 25. You certainly don't have to, but you could. And when you multiply that out, what do you get? You can grab a calculator if you want to. It's fine. Somebody said, what'd you get? 900 is correct. Good job. 900. 4 times 5 is 100, and then 100 times 9 is 900. So the least common multiple is, in fact, 900. Now, just like we did, I didn't mention in the last 2 problems, but just like we did with greatest common divisors, we can at least look at the 900 and make sure it really is a multiple of the numbers we had before. Right? So how would we do that? How would I make sure that 900 is a multiple of 90, is a multiple of 50, is a multiple of 20? What would I have to do? What could I do to make sure that they really are multiples?
You could just see it, like, divide it.
Yes. Yeah, you could take the 900 and divide it by 90. Take 900 divided by 50. Take 900 divided by 20. And if it's really a multiple, then every time you divide, you get a whole number answer, right? No remainders, no decimal points, stuff like that. Very good, Sydney. Okay, everybody good with that one? Okay. I told you division by primes was one of my favorites last time, and it's still my favorite for this one too. So let's jot this one down, division by primes. Okay, are we getting close? All right, let's just talk through this a little bit. The first thing we're going to do is write the numbers in a row. And then the second thing is to look for common prime factors. Any common prime factor we can divide by that prime factor. We usually start with the smallest and go to the largest if we can. The third thing, and this one feels awkward, let me ignore the part that says note inside of there for a moment, and you'll see what happens when we get there. We divide the quotients by a common prime factor. All right, so we divide those. Yeah, okay, I think I already said that. And then number 4, we repeat that step 3, until no other common factor can be found. And then the least common multiple is the product of the primes in step 4. And I know that and I shouldn't even say necessarily product of the primes. There are things that aren't going to be prime in that potentially, and I'll show you when that happens. Okay, so let's go back to that part in parentheses. The part in the parentheses is telling us what we would do if we had 3 numbers or more, and that's what it's really doing. Now, it's saying that there is an additional sort of step to do when we're finding least common multiple that we didn't have when we found greatest common divisor. And so that's what you're going to see happen, and I do have an example that has 3 numbers, so you can see that happen and how that plays out. A couple things to be aware of is that, well, I'll show it to you when we do it. This one's a little bit less obvious as to how it's different when we're writing it down, but it's very obvious when we do the problem. All right, so we have numbers. We have 90, we have 100, and we have 20. And the first thing we're going to do is we're going to write them in a row, side by side, so to speak. And what we're going to do first is exactly what I would do with greatest common divisor. I would ask myself, what number goes into all of these numbers? Smallest prime number, 2. And we'll divide each of them. And I would get 45, 50, and 10. Now these numbers are not all divisible by 2 now, right? They're not. They're not divisible all by 3. What's the next prime number? 5. Are they all divisible by 5? Yes, they are. So if I divide 45 by 5, I get 9, 50 by 5, 10, and 10 by 5, 2. If we were finding greatest common divisor, we would have to stop because 9, 10, and 2 do not have anything in common, right? And the answer would be the 2 times the 5 that's on the left-hand side. Everybody good with that so far? For least common multiples, what we do next is we look to see if any of the numbers, even if not all 3 of them, but if any of them, in fact, have anything in common. Are there any 2 numbers that have a common factor? 10 and 2 do. And what do they have in common, Amanda? 2. So I'm going to put a 2 out here. Ignore my 9 for a second. 10 divided by 2 is 5, and 2 divided by 2 is 1. So you might be saying, okay, but what about that 9? He didn't divide. And you're right. And so what this does over here is it tells me what we have to do. It says any of the numbers, there it goes. The number is that is not divisible is simply relisted. So the 9 that didn't divide by the 2 simply gets rewritten. That's all that happens. Now you'll notice that's where I said, oh, it's not really exactly the product of the primes. Let's just say the product of all factors. That's probably a better description here. The product of all the factors. Sorry, I should have left it there. They're not necessarily all going to be prime. In particular, the number 9 here is not prime, correct? All right, so in greatest common divisor, what we did is first of all, we wouldn't have this 2, 9, 5, 1. We wouldn't have this last step. We would have simply multiplied the 2 numbers on the outside, right? Okay. With least common multiple, what we do is we multiply all of the numbers all the way around. So we multiply the 2, the 5, the 2 that's there, and then also the 9, the 5, and the 1 on the bottom. So they aren't necessarily all primes. Sometimes they are. They could be. But the 9 here isn't, and that's totally cool. There's no reason to mess with it, okay? So we're going to multiply 2 times 5 times 2 times 9 times 5 times 1, and we're going to find out that is our least common multiple. So somebody grab a calculator, multiply those out for us. 2 times 5 times 2 times 9 times 5 times 1. What do you get? It's 900. And we could check just like we did on the last one to make sure that 900 really is a multiple of each of these by simply taking 900 divided by them and making sure it divides evenly. I like this in large part because the answer is just all right there together. Right? Everything's circled in orange. It's all just right there. The only thing that you have to be careful of, especially with least common multiple, is remembering that you still have to factor out this 2. If you do not factor out this 2, your answer would end up being 1800 actually, which would be larger than the least common multiple. It'd be a common multiple, but it wouldn't be the least common multiple. You guys with me on that? So you have to remember to factor out anything that even two of them have in common. Okay, we have one more part to take a look at, and one more, it's really a theorem to take a look at in this section. This is called the greatest common divisor, least common multiple formula. This tells us that there is, in fact, a relationship between greatest common divisors and least common multiples. And the relationship is such that if I multiply the greatest common divisor times the least common multiple, it's the same thing as the product of the two numbers. And that's an awfully handy fact if you'd already done one of them and you wanted to find the other one. If you already knew the greatest common divisor and you knew the two numbers you were working with, you could use that to find the least common multiple. And in fact, that's what we're going to do on the next problem. We're going to take an example that we'd already had. It was the example we did at the very end last time from the Euclidean algorithm. In the Euclidean algorithm, we found the answer to this one, the least common multiple of the numbers 72 and 126. So go back to example 4 and take a look for me and let me know, what did we find the least common, not the least common multiple, I'm sorry, greatest common divisor. What did we find the greatest common divisor was between 72 and 126? It was 18. We already did that. We did it with Euclidean algorithm. There's nothing special about the Euclidean algorithm. We could have done it with any method and still gotten the 18 and used this, okay? Nothing special about that at all. So what this formula says then is that the least common multiple times the greatest common divisor should be the same thing as the 72 times the 126 that I'm being given. And I know that the greatest common divisor is 18. So somebody tell me, what am I going to have to do to solve this for the least common multiple?
Divide the product of 72 and 126 by 18.
All right, so I'm going to have to move that 18 to the other side, and I do that with division. So my least common multiple, if you grab your calculator, should be 72 times 126, hit enter, and then divide by 18. You don't even have to hit enter on some of your calculators, but a few of you do. So what do we get? It's a large number, right, Cassidy? What'd you get? 504? Do I have a second on that? Yep. Okay, great. So we didn't have to go through any other algorithm. We didn't have to do any prime factorization. We didn't have to do anything because we'd already done one part of this problem, the greatest common divisor, when we did it last time. Is that good? It's a very handy relationship to know. All right, I wanted to show you a couple applications of where these are really used in real life. And this is a really good example. I want you to take a look because it does not say on either of these problems, find the least common multiple or find the greatest common divisor. It won't say that. It's up to you to know that that's what you have to find. So let's read through the problem and we're going to make the decision first. What am I looking for? Greatest common divisor or least common multiple? Two bike riders ride around in a circular path. The first rider completes one round in 12 minutes. So imagine like going around like a track at the football field or something like that, okay? Something like that. One of them is able to complete the round in 12 minutes. The second person completes the round in 15 minutes. If they both start at the same place and at the same time and they're going in the same direction, and we do need all of those conditions or this all falls apart, okay? If that's happening, and then they continue at a consistent pace, okay, those of you who run or bike or swim or something like that know that that's actually not always true, right? You don't always continue at a consistent pace, but that's the assumption we're using. The question is, after how many minutes will they meet again at the starting place? So, your first question to answer, to ask yourself is, am I needing to find a greatest common divisor or am I needing to find a least common multiple? Okay, I think I heard both.
I would say greatest common divisor.
Think greatest common divisor, least common multiple. Okay, so this time it is least common multiple. So Amanda, can you tell us why you were thinking it was least common multiple?
Because I just thought of like them going around the track is like a rod. And then so you have to figure out how many rods you need for them to be at the same place.
Okay, so Amanda's thinking of it in terms of a concrete picture of what's going on. let me kind of talk through why greatest common divisor doesn't make sense for the problem. So if I were finding the greatest common divisor, I would be finding a number that divides 12. So let's pretend the number's 3. In fact, 3 would be the greatest common divisor for these numbers, 3. So if 3 is the greatest common divisor and 3 is what I'm answering, then what I'm saying is that after 3 minutes, they meet at the same place. That doesn't quite make sense because after 3 minutes, they aren't at the starting place. Either one of them, are they?
That's what confused me because I was thinking that it was like 12 minutes total and 15 minutes total that they
It is.
like.
But then they're going to keep going after that 12 minutes. So it's
Yeah,
like
that's what I thought.
they go around the circle in 12 minutes, and then they're going to go around the circle again, and it's going to take them another 12 minutes for a total of 24. Well, how are 12 and 24 related? They're multiples. Okay, so this one is a multiples problem. So what kind of method would you like to do to find the least common multiple of 12 and 15? You guys tell me. What method would you like to do?
Timeline? Or not timeline, but number line.
You want to do a number line. Okay, we can do a number line. All right, so if we do a number line, so that's like the numbered rods or the colored rods method, number line or colored rods method. So if I did a colored rods method, I would go from 0 to 12. What would come after 12? 24, yep. What's after 24? 36. After 36? 48. After 48? 60. We'll go one more. After 60? 72. Okay, so I used a black coloring as I did that. I'll use orange for the other one. So the second person is hitting back at that starting line every 15 minutes. So 15 is his first value, which is somewhere in here, his or her. So they're hitting here at 15. What comes after the 15? They're going to hit again at 30, which is somewhere in between here. So here's our 30 marker. What comes after 30? 45, is that what I heard? So at 45, we have a mark. What's after my 45? 60. And I was already hitting back at the starting point at 60 with the 12-minute person, right? So now I hit back at the starting point at 60 with my 15-minute person. Now they've done different amounts of laps, right? One of them went how many times around? The 12-minute guy, how many times around did he go? I think he went 5, right? Because he went to 12, 24, 36, 48, 60, 5 times. How many times did the 15-minute person go around the track? 4 times, actually. So they go around the track a different number of times, but they do end up back at the starting point at the same place at 60 minutes. So the least common multiple is, in fact, our answer, and the answer to the question then is at 60 minutes. And as always, if there's context, we're going to use context in the answer, so that's why I have the minute marker there. Okay, at 60 minutes, they both end up back at the starting spot at the same time. Now let's just go through real quick, and let me make a couple of comments. They have to start at the same place, right? Or this wasn't making any sense. They have to go the same direction. Otherwise, they're crossing paths at other places, right? Yeah, so they need to be going the same direction. What happens if they lose pace? What happens if somebody slows down or speeds up? All the minutes change, right? So those are why I need those conditions for this to actually make sense in terms of the mathematics we just did. Okay? All right, another question for us. Dr. Hands makes cupcakes for her students. She makes 20 chocolate cupcakes and 24 vanilla. More likely she made 20 and somebody ate 4 of them before she came to school, just so you know. Just so you know. But all right, so there's 20 chocolate cupcakes and there's 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate, but only one type of cupcake on each plate. And we'll talk about why these conditions are necessary as well. What is the greatest number of cupcakes she can put on each plate? Okay, so we first have to decide, is it greatest common divisor or least common multiple? So which one is this? Definitely greatest common divisor, right? We're dividing up the cupcakes. That's a divisor. Definitely a divisor question. So let's actually find the answer to the question, and then we'll talk about contextually what that looks like in terms of our plates of cupcakes. So greatest common divisor. How do you want to find the greatest common divisor of 20 and 24? Okay, we're going to do my favorite method since nobody's clamoring to do anything. Do you remember what I said my favorite one was? Division by primes, 20 and 24. What number do 20 and 24, first prime number, do they both divide by? 2. And that would give me 10 and 12. And this also then divides by 2, which gives me 5 and 6. And 5 and 6 are relatively prime. That's the vocab we use for that, right? They don't have anything else they divide by. Now, if I wanted least common multiple, I'd multiply 2, 2, 5, 6. But I don't want least common multiple. I want greatest common divisor, so what do I multiply? Just the 2 and the 2. So the greatest common divisor here is actually 4. And so the answer to my question is that it's 4 cupcakes. So let's think about the picture of what's going on. There's a bunch of cupcakes, and we're putting them on plates. I need all of the chocolate on one plate and all the vanilla on one plate, because if I start mixing them together, I simply have 44 cupcakes, and I could put any number of cupcakes on any plate as long as it divides 44. Right? That wouldn't necessarily force me to have cupcakes that had 4 on a plate. In fact, I could have an 11 on a plate, and that'd work just fine for if I had 44 cupcakes. So I need to isolate only cupcakes that are chocolate and only cupcakes that are vanilla on the plates to make this actually work. Okay, that's how I get divisors of specifically the 20 and divisors specifically of the 24. Anything else I want to make comment about? That's usually the issue that students don't recognize in this one, is the fact that we have to isolate them separate them as we're working. I think that's it on this one. Any questions on this one? All right.